Hello. Today I'll be walking through my code for predicting term deposit subscriptions using the bank marketing dataset. I'll break down the four main parts of my modeling pipeline to explain how I maximize performance and then dive into my diagnostic learning curves to prove the model is optimally fitted. Submissions for this project are evaluated using the ROC-AUC metric. Because term deposit subscriptions are highly imbalanced, optimizing for ROC-AUC forced me to focus on the model's ability to rank probabilities correctly rather than just chasing a misleading raw accuracy score. In part one of my code, I focused on data representation. Rather than feeding raw data directly into the algorithms, I engineered golden features. For instance, a raw bank balance doesn't tell the whole story, so I engineered a balanced age ratio to give the model context on financial stability relative to client's life stage. I also created a financial stress indicator combining negative balances and active loans. Equally important was handling features like P days, the number of days since the client was last contacted. I explicitly cleaned the -1 placeholder values to prevent the tree-based models from incorrectly grouping clients who were never contacted with clients who were contacted yesterday. Throughout this block, I rigorously checked for target leakage, ensuring the model had no access to future information like current campaign call durations. Moving to part two, I built custom objective functions for Optuna to systematically tune my LightGBM and XGBoost models. Inside these functions, you can see I defined a specific search space for hyperparameters, such as suggesting integers for max depth and floats for the learning rate. Crucially, to evaluate how good a set of parameters is, the objective function uses an internal threefold stratified cross-validation loop. It trains the model on the suggested parameters and returns the mean ROC-AUC score. This ensures the tuning process is driven entirely by the competition metric, completely avoiding single-split holdout variance during the search. In part three, I launched the actual optimization study. Instead of relying on a slow, exhaustive grid search, Optuna uses Bayesian optimization. Over 30 trials, it learns from its past attempts to intelligently navigate the hyperparameter space, aggressively hunting for the parameters that maximize that cross-validated ROC-AUC score we defined in the objective function. Once the optimum parameters were found, part 4 executes the final training. I unpacked the best params dictionary directly into my LightGBM and XGBoost classifiers. I also included a CatBoost classifier with balanced class weights to capture a wider diversity of tree building patterns. Finally, I blended their prediction probabilities using a 40-40-20 weighted split to create my final submission, which achieved a highly competitive score of 0.7955. Then I did some cross-validation, and I finally I wanted to explicitly assess the bias variance trade-off. However, leaderboard performance is only valid if the model's structural fit is robust. To formally assess the fit of my final pipeline, I completely abandoned single-split holdouts. Instead, I validated my tuned models using strict stratified five-fold cross-validation. As you can see in my diagnostic outputs, my optimized LightGBM model achieved a strong mean ROC-AUC of 0.7981 across all folds. More importantly, the fold level standard deviation was exceptionally low, just 0.0046. This tight variance mathematically proves that the pipeline is highly stable and not just memorizing the training data. Then I see the learning curve, and when analyzing the convergence slope on this graph, the behavior is exactly what we want to see. Early in the training process with fewer samples, there is naturally a wider gap between the training and validation lines. This indicates high variance or slight overfitting because the model doesn't have enough examples to generalize yet. To improve this fit and force that gap to close, the Optuna objective functions we saw earlier explicitly tested different regularization parameters. By finding the optimal balance for constraints like min-child samples and restricting the max depth of the trees, the model was prevented from building overly complex branches that memorize outliers. Because of this regularization, the convergence slope behaves perfectly. As more data is introduced, the training AUC steadily decreases while the validation AUC rises to meet it. The final numerical gap between the training curve and the validation curve at a maximum data is extremely narrow, just 0.0787 AUC points apart. Because both scores are high, tightly bounded with low variance, and properly converged, it proves that the classifier is neither underfitting nor overfitting. It is optimally well fitted to generalize to unseen test data. In conclusion, by systematically moving from targeted feature engineering to custom Bayesian objective functions and proving the fit with learning curve diagnostics, I built a highly robust and reliable classifier. Thank you for your time.